Okay, so let's get back to our discussion. So today I'm planning to sort of wrap up our discussion on singular value decomposition. That's one of these matrix approximation techniques that we introduced on Wednesday as a way to do PCA, right? So our main focus was to do PCA, which is principal component analysis. The reason we were doing principal component analysis was to embed data into or reduce the dimensionality of data, right? And that is one type of a latent variable model. But then we saw there's this mathematical notion of singular value decomposition, and then we saw the relationship between SVD and PCA and how SVD can be used to do PCA, right? In fact, what I said last time was that in most of the numerical packages or most of machine learning libraries which have PCA inside them, they typically use SVD to do the PCA, right? And in last class, if you remember, we kind of established the equivalence between PCA and SVD, right? So if you have a data matrix X, right, where each column X is a data object, right? Then if you want to do principal component analysis of that, right, you could do that by computing the, where is that? You can do that by computing the the covariance matrix of this, and then doing the eigenvalue decomposition of that covariance matrix, or directly you can do SVD of that, which is SVD is essentially you're decomposing your matrix into U, S, V transpose, and then you can look at the singular values or singular vectors, and those give you the eigenvector, those give you the principal components, right? So there's the equivalence there. So I want to just do a quick recap of that, and then we'll look at some applications of SVD. So SVD is a good way to do PCA, but then there are other interesting applications of SVD as well. So I thought, since we are looking at it anyways, we can sort of talk about their applications too, other applications too, right? So if you remember, we were talking about SVD, and then I said that there is this lemma called what is it called? Eckert or theorem, Eckert-Young-Mirsky theorem, which says that SVD gives you the best compression of a matrix, right? So mathematically, what we say is that if you take any data matrix, all right, in which each row of the data matrix is a data object, right? Then if you compute SVD, essentially what you're doing is you're trying to compute these sub-matrices. So let's go back here. So let's say this is your data matrix X, right? X is n cross D. And then by SVD, what we do is we do this transformation, which is we represent X as U times S times V transpose, right? And we assume that n is greater than D. That's just for simplification, but it also works in the other direction. But here we are assuming that the data is like this. You have more rows than columns. So essentially what happens here is now each U, so U and V are both orthonormal matrices, which means that each column in U, if you multiply it with itself, you get a value 1, which means that the magnitude of that vector is 1. And if you multiply it with any other vector, any other column in U, then you get a 0, which means they are orthogonal to each other, right? So that's the idea. And then S is a diagonal matrix, right? So what we say is that U and V are the left and right singular vectors, the columns in U and V, and S are the singular values, each diagonal value there, right? So you can think of, let's say, if I just take the first column of U, okay? So I'm going to represent it as this. So all rows, first column, right? And then I multiply it with the first entry in S, so which is the first diagonal value. And then I multiply it with the transpose of the first column of V, right? So this, if you look at this, right, so U will be a vector now because you're just taking the first singular vector. So this will be a vector of length n, so this will be n cross 1. This will be a scalar, so I'm just going to call it 1 cross 1. And this is going to be another vector, so this is going to be a d cross 1 vector, but so this is the transpose of it is 1 cross D, right? So if you multiply all of these together, you get a n cross D matrix. So you can think of it as some approximate version of X, right? Now if you think about the rank of this matrix, so I am assuming that in your linear algebra class you have encountered things like rank of a matrix, right? So what is a rank of a matrix? If I give you a matrix and if I ask you what is the, let's say, column rank of this matrix, it is essentially the number of columns that you can use to represent everything else, right? So for example, if you have a matrix like this, 4 2 6 3 1 4, let's put one more, 2 9, right? And this is 1 minus 7, right? So what you see here is that the last column is a linear combination of the first two columns, right? Because if you add these two up, you get the third column. So that means that the rank of this matrix is actually 2, because you can use 2 column vectors to come up with all the 3 vectors, right? And there are many other ways to sort of understand the rank, but this is sort of a very simple way. So in some ways, if you look at this matrix, right, the rank of this matrix will be 1, because you're using one column to recreate every column of X, right? So what SVD says is that if you compute this and you compute the Frobenius norm, which is just X minus X bar, this whatever this approximate value, and you compute what is called the Frobenius norm. Now a Frobenius norm is nothing but you take all the values in a matrix and then square them and sum them up, right? So if you take so f of any matrix A is essentially summation I j aij square, right? So this is just a way of computing the norm of a matrix, one number. So if you compute the norm of this matrix, which is that this is some kind of an error, right? So what SVD says is that if you use SVD to compute the norm of a matrix, or if you use SVD to compute the rank 1 approximation of a matrix, then this will be the minimum for SVD, because there are many other ways. There are many ways to compute to get rank 1 approximation of a matrix, right? For example, if I give you a matrix X, you can just take the first column, right? And that would be a rank 1 approximation of X. You can use the first column, right? And you can get a rank 1 approximation that way, or you can take the mean of the columns or median or anything, right? So there are so many ways to get the rank 1 approximation. What the Martin-Eckhart-Young theorem says is that if you use SVD to do this rank, approximation, that would give you the minimum norm. So that is why SVD is so useful, right? So in some ways that provides you the least amount of information loss while giving you the maximum compression, right? So if you look at this matrix, right, you can represent this matrix even though this matrix takes n cross d values. So let's say let n equal to 50,000 and d equal to 1,000, right? So if I want to store this matrix in memory, I would need 50,000 times 10, 1,000, memory locations, right? But instead of that, if I just maintain these things, then I need 50,000 plus 1 plus 10,000 entries, which is much less than this, right? So this is the benefit of SVD, that it gives you so much of compression while ensuring that the loss that you incur is the least among all possible compression. Any questions so far? Okay, very nice. And then you can move on. So maybe just taking the first column might not be very good. You might lose too much information. So you can take first few columns and it will give you some reasonable loss, right? So if you remember our demo last time, yes. 1,000. Sorry, well, 1,000 here, right? Yeah. Yes. What was the rank of the plane in this particular? Why do you have the rank of the? Well, we don't need the rank. All I'm saying is that when you use SVD, right, and if let's say you just take the first column, the first singular values, some first singular vectors to recreate your x, the rank of this matrix will be 1. I mean, it's not central to this whole discussion, but all I'm saying is that if you want to mathematically understand it, what SVD does is that by approximating x using this, it is essentially reducing the rank of a matrix. And what the theorem says is that SVD gives you the rank, low rank approximation of any matrix, right? So in terms of machine learning, maybe rank is not that important, but when you talk about matrices in sort of linear algebra terms, then you can use that information more, because essentially if you read more of mathematics, right, so rank is related to the dimensionality of the data, because the rank essentially means how many basis vectors do I need to represent all the data, right? So it kind of computes the intrinsic dimensionality of the data and so on. So that's sort of a, yes, right.
And also when we were calculating the rank for each bar, so we subtracted the second column from the first column. So how come did we choose the number 1 as the rank for the first?
Oh, okay. So this formula here, this is nothing to do with rank. This formula is just to compute the error or loss. So if I replace my x with any x bar, right, it could be anything, this lets you compute the error. So how much information have you lost? Okay. What this SVD ensures is that if you use SVD to come up with an approximation, then this would be the least error. Now, but you need to be little more specific there, right? Because I could have used just x here and then my loss would be 0, right? So what SVD says is that if you use SVD and compute the low rank approximation, so in this case we are saying rank 1 approximation, if I replace this with any other x bar which also has a rank 1, then SVD gives you the least error loss. Oh, okay. So here, this is just an example. So here I said that let's just take the first singular vector of u, first singular right singular vector from u, and first singular value, and compute the SVD. But yeah, so there is nothing preventing us from taking more than 1. Here, this is just an example. So I'm saying, why is the rank 1 of this matrix? Is that what you're asking? Oh, okay. So the rank of this matrix is 1 because it is being constructed by linear combination of one column vector, right? So every row, so this will have d columns, of course, right? But each column, you can think of each column as being created by a linear combination of this single vector. And that is the definition of rank, right? So how many columns do you need to recreate your matrix? That's a rank. So here you're only using 1. All right? Cool. All right, so let me go back to this example here, right? So I was showing you this we have done already. So let's say your x is this image, right? So x has n rows and d columns, right? I removed the color here. So this is your data. So if I use SVD on this, and I look at the first, so this is using the first singular values, right? So this is essentially what I was talking about. So this is what you get. So what SVD, because we are computing it as a product of one column vector with something else, this has a rank 1, right? So what SVD theorem says is that if you construct any other matrix of rank 1, the difference between that and the original data would be least for SVD, right? So in fact, I have a simple experiment here. So what I do here is I use different approaches to compute the rank 1 matrices. So for example, here what I do is I compute my new x hat by just randomly picking one of the columns and then just replicating it. Okay, so that's not a very nice way of doing, but this also has a rank 1, right? So then I compute the Frobenius norm, which is done using this call. Another approach is to just take the row means. I just take the row means and then I replicate it. Another one is I just pick one row and one column at random and multiply them. So these are all different ways to compute a rank 1 approximation of x. pick a column and row means and apply them. In all these cases, this is the error I am getting, right? And these are the approximated values. But if you use SVD, which was here, the error of this would be the minimum. In fact, I'm sorry, somewhere I need to also print the SVD error. So this is my X, right? This is my doing the SVD. And this is, I approximate it. So this is my Z, which is sort of like that X hat. And the error is this much. So the Frobenius norm is this. And these are the other ways to compute the SVD. Oh, sorry, to compute rank 1 approximations. And if you see, all of them have higher error. Ooh, is it higher? Yeah. So the lowest error that you would get is by doing SVD because of that theorem. There's not, you can't do better than that. All right, so that is the idea. And even sort of illustratively, you can see that all of these approximations do not really capture much about the image, whereas this one does have some information in it, right? So for example, there are these dark spaces which kind of coincide with the dark space in the original image, right? And then later I showed you, if you use higher number of singular vectors, right, which means that you can use the first 5, that means you are saying I'm doing the rank 5 approximation of the matrix, you get a better sort of approximation. If you take more, in fact, if you do 50, you get pretty close to your actual image, right? So that is sort of the power of SVD. Any questions so far? All right, so this is what we talked about. All right, now I quickly want to talk about applications of SVD before we move on. Sorry, I had a slide here, I don't know where it went, but anyway, so SVD, of course, we said that it is useful for doing PCA, and it is also useful for doing compression of data, but we can also use it for one more thing. So there are many other applications. You can do it for topic modeling. So if you have text and you're trying to infer hidden topics in the text, you can use it. That technique is called latent semantic indexing. You can also use it for what we call recommender systems. Okay, so I'm going to give you a quick sort of overview of how to use it, right? So you can think of SVD as a technique to do matrix completion. Okay, so if you have some matrix, if you compute its SVD and then take some low dimensional, some fewer singular values, and then you recreate your X, right? Some of the values that were 0 in your original matrix would get some value there, right? So that is known as matrix completion. And in the case of recommender systems, you can use it as a technique. So let me just introduce what a recommender system is, right? So recommender system is sort of a tool that is used to tell you what you should buy. So you probably are familiar with that in the context of Amazon, right? So if you go to Amazon, they often tell you, okay, you bought a lawnmower, maybe you should also buy, something else. So that's sort of a recommender system. So there are many ways to do that. So one of them is what we call collaborative filtering. So for example, what you would do is, what Amazon would do is that they will say, okay, here is a customer, and this customer has bought this thing, and this thing. So 4 different items. And there is this another customer who has also bought these 4 items, right? So they link these 2 things. Okay, whatever this guy has bought, this other person has also bought, right? Then they say, okay, now this other person has also bought this 5th thing. So then say, okay, maybe this person should also buy that 5th thing, and so on, right? So that is one way to do it. Another way to do it is to do more sort of a mathematical approach. So that is where sort of these methods like SVD come in. And then there are other methods as well. But so I'm going to show you how to use SVD. All right. So there's all this text here which you can read. But the idea is that you have this data matrix X. Okay. And in this data matrix, your rows. Oh, sorry. Your rows are essentially people, right? So Jim, Brenda, Johnny, Joe, and so on. And your dimensions are these products. Okay, so these are the things that they like. And then you have ratings. So Jim likes chocolate with a rating of 1, Chris with a rating of 2, and so on, right? So this is what you know about people. What you want to know is fill out these missing values, right? So you want to find out, okay, how much does Jim like TV? Or how much, I don't know what like TV means, but how much does Jim like peanuts? And so on, right? So that is the problem of recommender systems, right? And then you can replace it in other categories. So this could be like Amazon, this could be Netflix, right? Where you could have these people here, and then these are the movies, and these are the ratings that they give, and you want to fill the rest of them out, right? I think in this example, what I'm going to do is I'm going to make it binary. So you either like something or do not like something. But in case of SVD, or in general case, you need to have ratings as well. But let's say for simplicity, we have made this, right? So this is the data that I showed you earlier in sort of a NumPy array. And then here I have made it sort of binary. Okay, so we're going to work with this one. So what we have done here is I've replaced the missing values with 0, which means I don't know what it is, right? So, and we want to fill these values. Okay. So in recommender systems, what we can do is we can take our X, which was that matrix, right, and do SVD, right? And then the first thing we do is let's study the scree plot. So we see how many singular vectors do we need to take. That we can do by just plotting the the singular values, right? So that's what I've plotted here. I've plotted the square of singular values because if you remember from Wednesday, the principal component, that lambda, is related to the singular values as a square function, right? So it's a square of that. We can use that to say, okay, let us take the first two. We say, okay, the first two are enough. After that, you don't get much benefit. So you take the first two and you recompute your x prime or x hat, right? Which is just a product of uv and the diagonal values, right? So this is the x hat that you get. So what you see here is that the original x was this, and by doing SVD and taking the first two components, we have filled out some of the values, right? So this helps you do little bit. So you don't fill out all the values because it depends on how the matrix is, but you do fill out, for example, this person, whoever this was, right? Earlier we didn't know much about this person, right? Here it is, about Karen. So Karen, all we knew was she likes chocolate, TV, lemonade, and orange juice. But by doing the matrix filling approach, now we know more about it. Like she likes whatever these things more as well. Right? So that is sort of the basic idea behind using SVD for recommender systems. But then there are certain drawbacks about SVD. So one of them is that there is no, so if you look at these, right? So these singular vectors tell you something about these things. So for example, this is the first singular vector, left singular vector, and it tells you, okay, for the first component, these things are important. So fine. So the fifth person, whoever the fifth one. So what that tells you that the first singular vector gives more importance to Rosa's preferences, right? And same way. And then you can also study the right singular vectors, for example, this one. And then this way you can understand that, okay, in this one, these correspond to the attributes. So they say, okay, this one probably gives some importance to these values, which are TV and peanuts and so on. So that's the idea. But there are some drawbacks behind using SVD. One is, of course, you get all these negative signs, which become hard to interpret. So what does a negative sign mean, right? What does it mean that this singular vector has 0.4 here and minus 0.7? So there are other methods like non-negative matrix factorization where you force the output to have only positive values, and so that is one way to improve it. There's other issues with SVD. So some people have argued that why do we put a 0 here, right? 0 doesn't really correspond to a missing data. So then there are other methods which directly sort of work with missing data and so on, right? Some people also say, okay, some recent papers I have seen, they say, okay, the fact that Ruby, the chocolate is missing for Ruby might mean two things. One is maybe she's never tried chocolate, or maybe there is some reason there is a missing value there. Maybe she doesn't like chocolate at all, right? So then there are methods to understand that as well. But a basic, very vanilla form of recommender system is like this. So you start with a data matrix which has a bunch of zeros, which means missing values. You do SVD on that, take a few singular vectors by studying the scree plot over here, and then recreate your matrix, and then you get some values filled out. And that's kind of what you want. Any questions so far? Yeah. Or in what? Right. Oh, okay. So the process is this, right? So you first take your X, you do SVD, right? Then you say, okay, how many singular vectors do I need to choose? That you do by studying this plot, right? Which is basically the square of the singular values. And let's say you chose these first two, right? So then you take, so this is the first singular vector, left singular vector, right? Then if you are trying to understand what does this mean, how do you interpret this, right? So these singular vectors, this vector is associated with your rows, which are people, right? So then you see which one has the higher value, so 0.8, and this corresponds to rows, so like that. So this is a way of interpreting it. There's a question here? Yeah. You mean just putting any value here? Oh, I see. Why is it important? All right. So see, mathematically, SVD ensures that the loss between this and this is minimum. So that is one way to understand it. But more from recommender systems, if you want to understand it from recommender systems, what you see here is that this value, right, is essentially a combination of these factors, right? So what these factors tell you, essentially you are trying to reduce the dimensionality of your data here, right? So you're saying that, okay, I am going to map all of my data in this two-dimensional space where the first basis vector is this and second basis vector is this, right? So you're kind of bringing in the relationship between these products and items together. I can explain more maybe later. This is a little more sort of recommender system kind of, you have to get into that mind frame. But yeah, so somehow it is trying to bring out the best linear combination of these factors, right? So for example, you are essentially trying to figure out, okay, how much does Karen like TV, right? So in some way you're saying, how much does Karen like TV? You're kind of posing the question, okay, how much is Karen like other people who like TV, right? So it has some relationship to the earlier method that I said, that collaborative filtering, but in a more mathematical way. Any other questions? All right, good. Yeah, I guess that was all I wanted to talk about singular value decomposition. It's a very interesting method. So, in future, I'm sure if you're pursuing a career in this area, you would come across this in one form or another. Okay, so I want to move to a new topic today, which is sort of going to be our last topic for this course. And ideally, I should have talked about this when we were talking about clustering, because essentially we are going to talk about another clustering method. So maybe next year I'm going to merge them both. But I did want you to sort of attend Suchit Smith's lecture, because he talks about graphs and everything. So that gives you a better idea of what we are doing. But the idea here is that, we have talked about clustering as a problem, right? So clustering is a problem where you give some data, right, bunch of data without any labels, and you want to partition it in some meaningful clusters, right? And we looked at one clustering algorithm, which is k-means clustering algorithm. But then there are many more, right? So in fact, before talking about this method, so today we are going to talk about one method, but if you go to this sorry, this is the same thing here. So if you go to this workbook that I have, Spectral Clustering Demo, in the end, I have this comparison of many clustering algorithms. This I pretty much copied from sklearn. So they have this whole tutorial, right? So what they do here is they create a lot of data sets, and then there are a lot of clustering algorithms here, right? So there is k-means, there is something called affinity propagation, there is mean shift, there's spectral clustering that we will talk about today, and then there are other methods like WAR, dbScan, BIRCH. So if you pick up any book on clustering or a survey, you will see all of that, right? So here, if you run this algorithm, this is what you get. So there are 4 different data sets, and I ran these 5 different clustering methods on them, and each one of them has some slightly different performance. So the point behind this exercise is to show you that even for these simple data sets, right? So these are all data in 2-dimensional space, and what you see is that in each of this data set, at least in the first 3, there is some meaningful notion of a cluster, right? So here you have these clusters, here you have a cluster, here you have a cluster, here you don't. Here this is just a bunch of points uniformly sampled, right? If you run all of these algorithms, they will all give you some result, okay? And in some cases, some will work well, some cases, some will not, right? So for example, let's look at this data set, right? So this is basically 2 concentric circles. K-means does not quite capture the clusters, right? Because it kind of just splits into 2, and that is because that's how k-means is, right? There's another algorithm called affinity propagation, doesn't work very well at all. See, k-means, the point is that in k-means, you have to specify how many clusters you want, right? And if you go up in this particular example, I have specified that I need 2 clusters, but even then it wasn't able to find it. Affinity propagation is an algorithm that does not require you to specify how many clusters you want, but then in this case you see that it actually fails because it kind of splits it into many clusters. There's an algorithm called mean shift that completely fails, and then there's an algorithm called spectral clustering, which works pretty well, right? Even this word algorithm works very well as well. So we are going to look at so then you look at all of these other examples, you see that in all of these, at least in 2 of these, spectral clustering and word work very well, whereas all these other ones sort of fail. In some of the other settings, actually other ones work well. So work well and so on. The interesting part is here, right? So this is a data with no clusters at all, right? And what you ideally want is your algorithm to tell you that there is no cluster, right? But some of these algorithms, they do find whatever you ask them to find. So for example, these 2 algorithms, they just do something. This one is nice, word, because it doesn't find any clusters at all. Mean shift also actually does pretty well here, and so this is the idea. So this is a sort of a nice exercise that you can try if you download this workbook. By trying out these different clustering algorithms, you can use different parameter settings and so on. You can get other data sets as well. So one good thing about this what is this sklearn is that it has a lot of these sample data sets already built in. So for example, here I use these 4, and then there are many more. So there is a package called data sets, and everything is in there. So you can try all of that and see, right? So this is sort of the variance in the behavior. Yes, Dave.
Looking at that, like the K-means clustering, the K clustering, and the word, for instance, why would you even bother with K clustering if you have something like word that's going to do consistently good throughout?
Yeah, so that's a good question. So the question is, why would you use word? Or why won't you use word in all the settings? Well, so this is actually just a small subset of possible samples. So I can always create a sample data set in which word would fail completely, right? The other thing is, if you notice on these, bottom right corner, this is the runtime of these algorithms, right? So if you see, word actually runs very slow, even for these small data sets, right? These data sets don't have more than a few thousand points. It takes close to a minute, or sorry, close to a second to run, whereas some of the other ones, or at least k-means, is fairly fast, right? So then sometimes that becomes a consideration as well. But yeah, so at least for this setting, it seems like word is sort of a very good algorithm, but it might not be true every time. Any other questions? Okay, all right. So as I said here, right, so we have already talked about k-means, you know how that works. And I'm going to talk about spectral clustering a little more. And then, feel free to go and explore the other methods as well. Right. So the reason spectral clustering is interesting is that, of course, it works on general data, right? You have data in d-dimensional space, you can use it, but it also works for graphs. Okay, so in fact, it was originally meant to do clustering in graphs, and then we'll show you how to use it for data as well. So here is the general idea. So if I have these n data points, x1 through xn, and let's say I have some similarity function sim that lets me compute a similarity between any pair of objects, right? So this could be like inverse of Euclidean distance or so on, cosine measure. So there are so many ways to compute the similarity, right? So let's say S is a matrix that you get by computing the similarity. So this is kind of like a kernel matrix, right? Now from that similarity matrix, I can create a graph, right? So if you remember, now what is a graph? A graph is basically bunch of nodes connected to each other, right, by edges, right? So a graph can also be represented by something called an adjacency matrix, where the ijth, so the adjacency matrix will have n rows if you have n nodes and n columns, and each ijth entry tells you if there is an edge between those columns, between those two nodes or not, right? So you can construct that kind of graph from data like this. So you compute your S, which is this similarity matrix, okay, and then you compute an adjacency matrix W, in which you use the similarity to put an edge. Okay, so there are many ways to do that. So one is you can put an edge between the nearest pair of objects. So let's go here. We're talking about spectral clustering. So let's say you have some data, right? Let's say it's in two-dimensional space. So you have some data objects like this, right? So what you do is first you compute your, so these are your x1, these are your dimensions, and these are all the x's. So you compute a similarity matrix, which is 10 by 10, right? And then you compute the similarities between all of these points, which could be just the inverse of their distances. Then from this, you compute a W, which is a adjacency matrix, in which one way to do it is you say, for every point, you say, what is my closest neighbor, okay, based on this similarity, right? So let's say for this guy, this is the closest neighbor. So you put a 1 there, right? And everything else is 0. And then so on. So you can put a 1 for its closest neighbor and so on. So that way, you construct this adjacency matrix. So in some way, what you're doing is you're transforming this data into a graph, right? Now you can generalize it a little more. So for example, you can say, instead of just looking at the first nearest neighbor, let me look at the first 2 or first 3 and so on, right? So that is the first part, which is creating a graph from your data, okay? And then we will come up with a clustering algorithm to now cluster this, okay? So now if you have a graph, right? So from now on, I'm going to not talk about the graph at all. We'll assume, sorry, the data at all. We'll assume that we have already converted my data into a graph. In this case, we are assuming it is undirected, because the similarity, we are assuming that the similarity is symmetric, the similarity function, which means, I see what you mean. So because we are doing the nearest neighbor, right? So my nearest neighbor might not be, I mean, I might consider somebody my nearest neighbor, but that one might not consider me as a nearest neighbor, right? You're right. So Yeah, so I think that is flexible. You can by just saying, okay, just enforcing sort of a symmetric property. But yeah, in general, it won't be symmetric by that algorithm. But let's say we do have a undirected graph, which means that you have a bunch of nodes now. And by doing that process that I explained, we have some edges. So maybe I connected these two. Now these are no longer in this 2D space, so don't think of these distances as the distance. Right? So somehow. Right? So now what does clustering mean in terms of graph? So in a graph, when you're trying to do clustering, essentially you're trying to identify these components, right? Because you want to say, okay, here is one component, here is one component, right? In a very simple scenario, maybe your graph looked like this, which means it already had two components, right? So then the task of the graph clustering method is to identify these two components, right? But in some cases, you might not have perfectly disconnected components. In that case, you want to identify the components which are sort of which are forming these clusters, right? So now today we are going to look at how to find these components given a graph, right? And I've already explained how to construct the graph from the data. But in general, let's say tomorrow you get a graph data directly. Let's say you get data of sort of a social network of this classroom, right? So you get all of your Facebook accounts is a node, and then they are connected if you are friends with each other, right? So now you have that, and now you want to cluster that. So essentially what you're trying to identify are these communities, right? So you can think of these in the context of a social network as a community. So this could be all the sort of, students who like clustering, and this could be all the students who are Bayesians and so on, right? Assuming that you form your Facebook friends based on that, right? So that is the idea. So now let's see how to get that. Okay. So the first thing we do is come up with an optimization function. Trying to identify in the context of a graph is cuts. So if you, I don't know if you have taken graph theory courses, but there's a notion of a cut in a graph, right? A cut in a graph is an edge that if you remove that edge, that graph breaks into two parts, right? So for example, in that example, that edge in between two clusters would be the cut. So you're trying to find, if you're trying to split the graph into k parts, you're trying to find k cuts in this graph such that this thing is satisfied. Now this is an objective function, okay? So the objective function looks like this. So you're splitting your graph into k parts, right? Such that if you take each part, the edges from that part to other parts are minimized, right? So that is the idea. So if you go back here, so for example, in this case scenario, right, you can split the graph into two parts anyways, right? So one of the way could be that I'm going to put a number. So I'm going to call this, and this in one in one part, and this in the other one. So this could be one possible cut, right? But this is not a very good cut. Why? Because the nodes that are within a cut, that are so one cut would be this and these points, right? But what you see is that there are too many edges going from the two cut to the one cut, right? So this is not a very good cut. You see? Whereas another cut would be, if I recreate this graph, if I call all of this in one cut and all of these in the other cut, then this is a good cut according to that objective function, because it is minimizing the number of edges across these groups, right? So that is the central idea behind this objective function, which is this. So you want, the objective is to divide the nodes into k groups such that the edges, this is essentially capturing the edges between across these groups, right? So you want to minimize that. However, there is a trivial answer for that. So for example, if you just want to cut it into two parts, one easy way would be to you just one cut would be only any one node and everything else is A2. Then you're minimizing the number of edges, right? So to address that trivial solution, you also weight it by the size of the cut. So you want big cuts. You don't want cuts to be containing only one node or two nodes, right? So you want to optimize over this function, which is you want to find the cuts such that the edges across the groups is minimized and each cut itself is big enough, right? So that is sort of the normalized min cut problem. So this is the problem that a spectral clustering algorithm will solve to find the right answer, right? So we're probably out of time. So next time I'm going to talk about the actual method that we use to get this, right? So if you think about this problem, right, this problem is equivalent to solving a 0-1 knapsack problem. So I'm sure you're familiar with what a 0-1 knapsack problem is, which is, you have a bunch of knapsacks and you identify which items go in what knapsacks to maximize this total value, right? The reason we show an equivalence to a 0-1 knapsack problem is because we know that this problem is NP hard, right? Which means that by definition that one also will be NP hard. In fact, this is NP complete, right? So however, there are solutions to solve it approximately, okay? And one of them is what we call spectral clustering. So next time I think I'm going to take maybe 5-10 minutes to sort of go over that. I have just a couple of slides there, and that will help you understand what spectral clustering is. Any questions so far? Yes. Directed? Maybe there is. Yeah. I mean, here I'm talking purely undirected. There might be a simpler solution. I don't know that. But if you're saying, yeah, maybe there is. So, but we are going to primarily talk about undirected graphs. And in those scenarios, solving the min cut problem is NP hard. Right? Any other questions? All right. Thank you very much. I'll see you on Friday, Wednesday. One announcement is a few announcements. Let me repeat. No recitation this week. Your gradients, final gradients course will be posted on Wednesday. Please make sure that you check them. Tell me if there's any discrepancy. And please take some time to fill out the course evaluation. All right? Thank you very much.